There's a common stereotype by non-cubers who think that anyone who can solve a Rubik's Cube is good at math. And while that stereotype isn't necessarily true, I started cubing about 3 years ago, and at the same time I started participating in competitive math. And there was one time where being a cuber actually helped me solve a math problem. Here's the problem. Jonas builds a large n by n by n cube using 1 by 1 by 1 cubes, each having the net shown. What is the smallest value of n for which the sum of the exterior faces of the n by n by n cube can be greater than 1,500? First, let's look at an incorrect way to solve this problem. This is a solution that I found online. First, recognize that the sum of the exterior faces of a cube is given by 6n squared, where n is the length of one side of the cube. Set up the equation 6n squared equals 1,500 to find the smallest value of n for which the sum of the exterior faces is greater than 1,500. Divide both sides of the equation by 6 to isolate n squared, resulting in n squared equals 1,500 over 6. Calculate the value of n squared to get n squared equals 250. Take the square root of both sides to find n, which gives n equals the square root of 250, which is approximately 15.81, which is greater than 15, meaning n has to be a minimum of 16. This solution is wrong because it assumes that every single face has a value of 1. So what is the correct solution? Pause the video and try it out for yourself. So if you have an n by n by n cube, let's think of this in terms of the corners, centers, and edges the cube has. So on any cube of any size, there are always going to be 8 corners. On an n by n by n cube, how many edges are there? If we look at a 3 by 3 Rubik's Cube, we'll notice that it has one corner piece, an edge piece, and then another corner piece. And because there's 12 edges in a cube, that's 12 edge pieces. But on something like a 4 by 4, that one edge piece gets split into 2 and becomes 24 edge pieces. On a 5 by 5, that becomes 36 edges. We notice a pattern here. The number of edges is always equal to 12 times the side length of the cube minus 2, or 12 times n minus 2 in parentheses. So how many center pieces does this cube have? On a 3 by 3 cube, in between all the other pieces, we have one center, and there's 6 centers because 1 per each face. On a 4 by 4 cube, that one center becomes 4 centers, and multiplied by 6 faces is 24. On a 5 by 5, that 4 becomes 9, multiplied by 6 is 54. This pattern is quadratic. So the number of centers on an n by n by n cube is going to be 6 times n minus 2 parentheses squared. So now we know how many of each piece there's going to be on a cube. So how much are each of the pieces worth? If we look at a center piece, the largest number we have on this net is a 2. So a center piece is worth up to 2 points. And because we're looking for the smallest value of n, let's assume the largest possible value for all of these pieces. On an edge piece, we're going to need to include 2 of these faces. If we look at the net, the 2 largest numbers on it are 2 and 1. But those numbers are on the opposite sides of each other, so it's impossible to include them both in the same edge. So the best we can do here is 2 and 0, which gives the edge a value of 2. So now the corner. For the corner, we're going to have to include 3 faces. Again, using the 2 and the 0, the largest number we can add to that is -1. So that gives our corner a value of 1. So we need to find the smallest value of n that gives this a value of 1,500. So we can now write this whole thing as an inequality. So we have the number of corners times the amount each corner is worth, 8 times 1, and then plus the number of edges times the amount each edge is worth, 12 times n minus 2 parentheses times 2, and then plus the number of centers and the amount that each center is worth, so 6 times n minus 2 parentheses squared times 2. We can create a new variable k and substitute that for n minus 2 to make things look a little less messy. So we have 12k squared plus 24k plus 8 is greater than 1,500. Subtracting 1,500 from both sides gives us 12k squared plus 24k minus 1,492 is greater than 0. We can use the quadratic formula on this inequality. X is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. Using the quadratic formula on this inequality gives us negative 24 plus or minus 266.53 over 24. And because this number needs to be positive, you can't have a negatively sized cube. It has to be plus 266.53. And that gives us a value of 10.105. Because we're looking for the smallest value of n for which this is greater than 1,500, we have to round up in this case to 11. And because we substituted a new variable k to equal n minus 2, in this case n would just be equal to k plus 2, so n equals 13.